All right. So in this part of the course, I'm going to talk about some of the ideas behind the algorithms for single particle reconstruction. And most of these algorithms are based on a probabilistic way of looking at single particle reconstruction. So I want to start by giving some mathematical background about the main ideas in probability theory that we'll be using. So the most fundamental thing we need to understand is the idea of a random variable. So this lecture is going to be about just defining what a random variable is and various associated functions that go with the random variable. So the actual formal definition of a random variable or of randomness is quite complicated. So I'm not going to go through the formal definition. We'll just intuitively try to understand what randomness is. So our working definition of randomness is something like this. So the main idea is that there is some sort of an experiment that you perform. And every time you perform that experiment, you make a measurement. And that measurement may either be an actual output of the experiment, or it may actually be some variable that is internal to the experiment. So you do the experiment, and you record this value, either of the output or of the internal variable, and you get a number, say let's 1.23. You then repeat the experiment as far as you can repeat the experiment under identical circumstances you do, and then you make another measurement of the same variable. And it turns out that you don't get the exact same number, you get a number that's different. So when you repeat the experiment over and over again, that same variable, the same value, actually gives you different numbers. When that happens, we say that that variable is a random variable. And say, if we denote that with x, then we would say that x is a random variable. Now, in this definition, the idea of an experiment is a little bit conceptual. So this may or may not be the actual physical experiment that you perform. It may be a part of that experiment as well. And let me illustrate what I mean by that. So in CryoEM, imagine that you purified a particle. So this is a ribosome. And then you take multiple copies of that particle and embed them in ice. But that embedding is random in the sense that the orientation of the particle inside the ice is not always in the same direction. So if you think of embedding of any one particle as a single experiment, then you can attempt to measure its random orientation by doing something like this. We associate an axis with the particle that is fixed with the particle. And then for every embedded particle, we can measure the tilt of that axis from the vertical direction, from the beam direction. So that's a single angle that we are measuring. And for different experiments, that is for different embeddings of the particle, that angle now takes different values. So that angle is a random variable associated with embedding of this particle in the ice. So the experiment here is not the overall CryoEM experiment that you're doing, but the embedding of a single particle inside that slab of ice. Okay, so now that we understand what a random variable is, I'm going to introduce a function that is associated with a random variable, and that function is called the probability density function. And the way you construct the function is in the following way. The first thing you do is you ask yourself, what are all possible values that your random variable can take? And in this case, because it is a scalar random variable, all possible values that x can take, the random variable x can take, are simply the real line. So any value that x actually takes is a point on that real line, and then different values are different points. The probability density function is a function defined now on the set of all values that x can take, which is the real line. And that function we denote either as p of x or p subscript x of x. The subscript x just tells you what random variable this is the density of. And the density function is defined in the following way. If you take any two numbers, a and b, on the real line, then there's a certain probability that when you do the experiment, the actual measurement x falls within that interval. And one way to think about this probability is simply to imagine that you repeat the experiment a large number of times. You simply count the instances where x falls within that interval. Then the fraction of times that that happens in that entire list is the probability that x is in that interval. The probability density function gives you this number as the area under the curve between a and b. So here is that function, and if you then simply calculate the area from a to b under that curve, that number is defined, that number gives you the probability that x takes values between a and b. So since that's an integral, you can imagine that there's also a derivative definition of the probability density function, and that is simply this. If you take that interval to be delta x, and you measure the probability that x is between a and a plus delta x, divide that by delta x, and take the limit as that interval becomes small, gets closer and closer to 0, that number you calculate is, of course, the density of the probability at a in that region delta x, and that we take as p of a. So this defines for us the probability density function for the random variable x, and the probability density function has two important properties, and they are simply that the probability density function is never negative, simply because the probabilities that you get by integrating it have to be always non-negative. And the integral of the probability density function over all possible values that x can take is 1. Very often, when we try to specify what the probability density function is for a random variable, we choose some convenient family of probability density functions. And these families are often parameterized by a finite number of parameters. And those probability density functions are called parameterized probability density functions. So here's a classic example of one. So I have a random variable x, and this notation says that this is a probability density function of the random variable x for the parameters mu and sigma. So that vertical line simply tells you that everything on the right-hand side of that are the parameters of that probability density function. And for a Gaussian probability density function, the functional form of the probability density function looks like this. The parameters mu and sigma have a meaning. Mu is the mean of the random variable x, and sigma squared is the variance of the random variable x. And this is what the probability density functions look like for different values of mu and sigma. So I'm keeping mu fixed at 0. If mu was non-zero, all of these densities would shift and be centered at whatever that non-zero mu is. So sigma of 1 gives me a probability density function that looks like this. If I decrease my sigma, so the random variable now has a lower variance, the width of that probability density function decreases, but because the area under the curve has to stay equal to 1, its height increases. And then, of course, when I increase my sigma, when I increase my variance, I get a broader probability density function, and its height is lower than what I have for sigma equal to 1. So more generally speaking, if you have a probability density function that depends on a number of parameters, theta 1 to theta n, usually we just write that entire vector of probability of parameters just as theta, and we define the parametric probability density function as px given theta. So in this case, theta is just mu and sigma, just I have two parameters for the Gaussian probability density. Okay. Now there's a slight generalization of what we've done so far, which is when we do an experiment, instead of measuring a single number, we measure a pair of numbers. So with every experiment now, we have associated a pair of numbers instead of a single number. So let's call the variable for the first number x and the variable for the second number y. And together, x comma y as a pair, we'll say is a multivariate or a joint random variable. And we can then try to define a probability density function for a joint random variable, the same way we did for a single random variable, which is first we think of all possible values x comma y can take. And because they are a pair of numbers, all possible values they can take, we can imagine to be the two-dimensional plane in which the value of x I can plot as a point on the x-axis, the value of y as a point on the y-axis. So each instance of x comma y that I get from an experiment is a single point in the plane. Then the probability density function is a function on the plane, and I'm going to denote that as px comma y, and these are the contours of that function. And just as we did for the scalar case, for the single variable case, I can define the probability density function as a function whose integral for x limits between a and b and c and d, which is for x and y together taking values in that square, the integral of pxy over that square is the probability that x occurs between the bounds a and b, and y occurs between the bounds c and d. And of course, we don't have to stop at just x and y. We can now define multivariate or joint random variables of any n set of measurements that we choose to make from x1 to xn. Okay, when we do that, the corresponding definition of the PDF is just a generalization from now 2 random variables to n random variables, which is this integral within the limits a1, b1, a2, b2, an, bn is simply the probability that the first component, the x1, falls between a1 and b1, the second component falls between a2 and b2, and so on, till the nth component falling between an and bn. And of course, again, just as in the scalar case, we can now think of parametric families of multivariate probability density functions. Again, the most popular one is the multivariate Gaussian, where if you take x to be your multivariate random variable consisting of n scalar variables, x1 through xn, then mu is the mean of each of these variables. Take sigma to be an n by n matrix whose ijth value is simply the correlation between xi and xj, which is you subtract out the mean, you multiply these two numbers, and then take their mean. So mu and sigma are the parameters for the multivariate Gaussian probability density function, and the probability density function has that formula. And in the two-variable case where x1 is x and x2 is y, the contours of that multivariate Gaussian look exactly like this, where these are symmetric or they are centered around the mean, and the orientation and the width of these contours actually depends on the contents of the covariance matrix of sigma xij. And of course, in the more general form, if you have x as a vector of n scalar variables, we can write the parametric form as before as probability of x given the value of the parameters theta. So theta in this case, in the multivariate Gaussian case, are just simply the vector of means mu and the n by n covariance matrix or correlation matrix sigma. Okay, so now that we are able to specify joint random variables and their PDFs, we can do something interesting with them, which is try to infer what the probability densities of each component of that multivariate density looks like. So the idea is this. Suppose I do an experiment where I am keeping track of two random variables simultaneously. So I have x and y as random variables. And as we saw on the previous two slides, we can write the joint density of x and y as some function in the xy plane. But then we can do something interesting with this. We can say, okay, suppose I give you the joint density of px and y, but now I choose to ignore y. I'm only going to look at values of x. That is, I'm only interested in x as a random variable, and then x will have its own probability density function, but surely it's related to this joint probability density function of x and y. And what's the relation between them? So it turns out the relation is quite simple. If you take the joint density pxy and simply integrate out the y variable, what's left turns out to be the probability density function of just x by itself. And this is what amounts to saying I'm going to take these joint values, but then completely ignore y and just concentrate on the probability density of x. And of course, you can do the same for y. You can take the joint density, integrate out x, and what you will get is simply the probability density of the y variable. So this calculation has a name. It's called marginalization. So we say that we take the joint variable x and y and we marginalize out y, and we are left with the marginalized density of x. So here I'm marginalizing out x, and I'm left with the marginal density of y. And of course, you can do that for more than two variables. So if I have n variables, x1 through xn, n jointly random variables, and I'm only interested in the density of the first k, then I simply integrate out the last the k plus 1 to xn variables from this density of x1 through xn. Okay, there's one other thing we can think about when we have joint random variables, which is, say we have two variables x and y. I can imagine that I fix a value of y, and I look at what the density of x looks like for that fixed value of y. So that corresponds to taking a slice through that two-dimensional probability density function, and simply looking at the distribution, the probability distribution of x on that slice. And that probability distribution of x for that fixed value of y is called the conditional density of x given y, and we write it this way. So the way you read this is the probability density function of the random variable x when y is fixed at the value that is on the right-hand side of that vertical bar. So you can ask, given pxy, given the joint density of x and y, how do I calculate the conditional density of x given y? And that turns out to be this very simple formula. So the conditional density of x given y is simply the joint density of x and y divided by the marginal density of y. And remember, the marginal density of y is just the joint density of xy where you integrate out x. Now it turns out that conditional densities have the same properties that probability densities have. They're always bigger than or equal to 0, and their integral with respect to the random variable. So remember, y is fixed. We're thinking of x as a random variable. So the integral with respect to the random variable is 1. So that's exactly the same properties that a probability density function has. And of course, instead of holding y fixed, we can try and hold x fixed, in which case we are taking this vertical slice through that density, and we are thinking about the conditional distribution of y given a fixed value of x. And that, of course, the calculation is the same as this. You just exchange the roles of x and y, and you get analogous formulae for the conditional density of y given x. And more generally, if you have the joint density of a bunch of x's, x1 through xn, and a bunch of y's, y1 through ym, you divide this by the marginalized probability density of y1 through ym, you get the conditional distribution of the x's given the y's. Okay. There's an important way of manipulating this formula that we're going to need. And basically, all it corresponds to is cross-multiplying py over to the other side. So if you know what the conditional distribution of x and y is and the marginal of y is, you can multiply the two and get back the joint density of x and y. And that holds for several random variables as well. Okay. So a very important theorem or a very important rule about conditional distributions is called the Bayes theorem or the Bayes rule. And what it does is it allows you to take the conditional distribution of x given y and in some sense invert that, so that you would then get the conditional distribution of y given x. And Bayes' rule says to go from here to here, you simply multiply by the ratio of the marginal distribution of x of y divided by the marginal distribution of x. And a similar formula holds for joint random variables where you have more than two. So the conditional distribution of x1 through xk given xk plus 1 to xn is the reverse conditional distribution. So probability of k1, k plus 1 to xn, conditioned on x1 to xk divided by the appropriate marginals. So just to tell you a little bit about who Bayes was, so Reverend Thomas Bayes was a British clergyman who wrote a paper first describing this theorem. But then later on, a lot of the mathematical implications of that were developed by a French mathematician, Laplace. This is the same Laplace who discovered Laplace's equation in heat transfer, Laplace's transform for differential equations, and so on. A very famous mathematician. Okay, so now that we have Bayes' theorem, we can talk about the central problem in single particle reconstruction, which is the problem of inferring or estimating what the structure is given cryo-EM particle images. And more abstractly, we can think of the problem in this way. We have some quantity y that we are interested in measuring. So y for us, for single particle reconstruction, will be the actual 3D density of the particle that we are trying to reconstruct. But unfortunately, we cannot measure y directly. Instead, what we do is we make a measurement. We do some experiment and we measure something else that is related to y. And the something else for us is going to be a bunch of cryo-EM images. The relation between y and x is random in the sense that if I were to create a new sample of the same particle and do another cryo-EM experiment, I would get a whole bunch of different x's. So the relation between y and x is a probabilistic relation. And the inference problem is, given x, to figure out what y actually looks like, or get some estimate of the probability, get some estimate of the particle density. And in some abstract sense, Bayes' theorem solves this problem in the following way. So what you do is you begin by saying, before I do an experiment, what do I know about the particle? And maybe you know something, maybe you know very little. But you specify your knowledge of what the particle is by constructing a probability density function over all possible particles. And that's called the prior. And by prior, we mean it's prior to the actual measurement. So that's the prior on y, the thing that you want to infer from the experiment. Then the process of experimentation, which is the relation between y and this random x, you specify by giving the conditional probability of x given y, which is simply a mathematical description of this experiment. So this description says, if I knew what the particle y was, what is the probability that I would see an image of a particular type? So this describes how the measurement x relates to y. And then our task is to go from this description of the experiment to actually inferring something about y given the measured x's. So the problem in some abstract sense is to go from the conditional density of x given y to y given x. And we know how to do that. That's just Bayes' rule. So Bayes' rule says you calculate y given x by multiplying these two quantities together and marginalize and dividing by the marginal density of x. And these quantities you can calculate very simply by first noting that if you multiply these two, you get the joint density of xy. You integrate out y, you get p of x, and that's what goes in the denominator here. Now, these steps may be quite hard to do, but in principle, at least mathematically speaking, we now know how to go from our prior knowledge of y to a posterior or an updated probability of what we think y is. And in some sense, all single particle reconstruction algorithms use this methodology. So a lot of what we are going to talk about in the remaining lectures is how do we actually calculate this, and then given py and given this posterior density of y given x, how do we choose a specific y from that density as the answer? Okay, we need one last notion, and that notion is of independent random variables. So I go back again to my two-dimensional joint density of x and y. So I have random variables x comma y. These contours are the probability density functions of the random variables. And what I want you to do is imagine what the conditional distribution of x given y looks like for different values of y. So, sorry, this should be my mistake. This should be a probability of y given x. So if I fixed x, the probability of y given x looks like this.
Hold on one second. So is that slide wrong?
That slide is wrong. Yes, okay, I'll give you.
Yeah, let's stop right now and correct it real quick. Okay.
Okay. All right. Yeah.